If your RAG grabs the wrong paragraph, add a small rewrite, retry, and verify loop, and require citations. You have a search or retrieval that sometimes returns the wrong paragraph. That hurts quality and trust. Today you will learn a compact pattern that rewrites a shaky query, retries retrieval, verifies evidence, and only answers when it can cite supports. You will be able to build a safer, higher precision retrieval-augmented generation flow in Python that is easy to inspect and tune. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced with simple, concepts-first Python that helps you solve bigger, real-world problems. Most RAG failures start with instability in the query and noisy retrieval. You ask a model for a fact, and retrieval returns a paragraph that looks plausible but does not support the claim. Success here means the system either returns a grounded answer with a citation or returns a clear not found. This pattern fits QA systems, documentation assistance, and knowledge-based front-ends where reliability matters more than showing something every time. The intuitive idea is simple. Turn the user request into stable tokens. Use those tokens to retrieve candidate documents by overlap. If the top hit is weak, try small rewrites of the query and retry retrieval. Then measure how much of the answer is actually supported by the retrieved text. If the support ratio passes a threshold, answer with a citation. Otherwise, say not found. This flow trades a little latency for large gains in trust. We will build a small pipeline that follows those steps with one toy corpus and a few simple functions. I will keep the code minimal so the logic is clear. We will see how token normalization, overlap scoring, retries, and a verification threshold all fit together. Now let us jump into the first piece, query normalization. This snippet normalizes a user query into stable tokens for retrieval. This snippet lowercases the text, splits on whitespace, removes common filler words, and applies a simple suffix strip to reduce variance. The top of the code shows the normalizer definition and the small stop word set. Next, you see the actual normalization call on a sample query to produce a list of tokens. The key idea is to make the same intent map to the same token set so retrieval scores are stable. If you make the stop words list larger, you get fewer tokens and more aggressive matching. If you skip suffix stripping, you preserve more surface form and may get fewer matches for related terms. Now we retrieve candidate documents by token overlap. This snippet retrieves the top documents by token overlap with the query. This snippet builds a simple inverted index from the toy corpus where each token maps to the documents that contain it. Then it computes an overlap score by counting shared tokens between the normalized query and each document. The code sorts documents by that overlap and returns the top candidates. The important parameter here is how many top candidates you keep for later steps. Keeping more candidates increases recall, but adds work for the retry and verification stages. The retrieval behavior is deterministic because the normalized tokens and simple counts avoid floating point variance. Next, we add rewrites and a retry policy to improve weak matches. This code retries retrieval across rewrites and selects the best match. This code generates a few small query rewrites aimed at focusing different parts of the user intent. For example, one rewrite might emphasize a named entity, another trims modifiers, and a third expands common acronyms. For each rewrite, the code normalizes and calls the overlap retriever. It records the top score and the associated document. At the end, it selects the rewrite that produced the highest overlap score. The retry loop raises the chance of finding a true supporting paragraph without heavy model work. If all rewrites return low overlap, you can either fall back to a broader search or stop early. Now we check whether the retrieved paragraph actually supports the claim. This example verifies support by overlap ratio with a tunable threshold. This example computes the ratio of query tokens that appear in the selected document as the primary verification metric. The code divides the count of matched tokens by the number of query tokens to produce a support ratio. There is a threshold variable that you can tune. A high threshold demands near-complete overlap and yields precise citations, but more not found responses. A lower threshold accepts looser matches and increases answer rate. The snippet also shows a simple keyword highlight to make it easy to inspect why a document passed or failed the threshold. Finally, we form the final reply or return safe not found. This snippet delivers an answer with citation or returns a safe not found. This snippet takes the verified document and composes an answer that includes the supporting paragraph as a citation label, or it returns a short safe message when verification failed. The code shows how to pull a document title or identifier for the citation, and how to assemble the final response text. It also includes a small guard that prevents returning partial or hallucinated answers when the verification ratio is below the threshold. You can make the citation more detailed by including a paragraph index or a character span if your corpus supports it. Mapping this toy flow to a production system is straightforward. Replace the simple inverted index with an ANN index for larger corpora. Keep the same rewrite and verify logic so that the system still demands explicit support before answering. Recap: it is a compact rewrite, retry, verify, and cite loop that forces evidence before answering. Use it when accuracy and traceability matter more than raw answer rate. One caveat is that aggressive thresholds increase not found responses and require tuning. For a next step, tune the verification threshold and measure precision at your target answer rate to find the best trade-off for your data. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.